Hello everyone, welcome to Civil Galaxy. In today's session, we shall see how to analyze a frame with the help of Kanis method when it is subjected for the lateral sway. So I have considered a problem over here where the height of the column AB is given as 4 meters and the height of the column CD is also given as 4 meters and the span of the beam BC they have given as 8 meters where at a distance of 3 meters from point B it is carrying an eccentric loading of 320 kilonewton. So from previous classes we have learned that whenever a frame is subjected for an asymmetric loading condition, then that frame undergoes the lateral sway. So in Kanis method we have learned the first step in analysis will be to calculate the fixed end moments. So we need to calculate the fixed end moments. So if we observe the frame over here, the column AB and CD, they are not having any external loading. So the fixed end moment from A to B and the fixed end moment from B to A, also the fixed end moment from C to D and fixed end moment from D to C will be equal to 0. Since there is no loading on AB and CD over here. Now if we take the span BC, we are having an eccentric loading of 320 kilonewton. So the fixed end moment from B to C, whenever we are having an eccentric loading, we know the formula, that is W A B square upon L square. Since we are coming from left to right, the formula is negative over here. So if we apply the values over here, W they have given 320 and the distance of A. So this will be the distance of A from point B, that is 3 meters. B, this will be the distance of B, which is 5 meters. So 5 square upon the total length. Now the length will be 8 square. So which will be equal to minus 375 kilonewton meters. So this is the value for fixed end moment from B to C. Similarly, fixed end moment from C to B will be equal to plus, because we are coming from right to left now. The sign convention will be positive, plus W A square B upon L square. So here this will be equal to plus 320 into A will be here this distance A from point B, which is 3 square into B is 5 upon 8 square. So this gives a value of plus 225 kilonewton meters. So this is the value for fixed end moments. So after calculating the fixed end moment, we know the second step will be to calculate the stiffness, which is represented by K, and rotation factors. The rotation factor, which is represented by U. So whenever we need to find out the stiffness and rotation factor, we know that from the previous classes we have learned we need to consider a table. So let us consider a table. First will be the joint, second will be members for that particular joint whatever we have considered, and for this particular member we need to find out the relative stiffness, that is K, and we have to take the total stiffness into consideration, which is sigma K, and finally we will consider the rotation factor, which is given by U is equal to, that is minus half into K upon sigma K. So this is the formula we have to use, we know that one. So if we consider the joint over here, if you observe we are having two joints, that is B and C. So we are having two joints B and C. If you observe a joint B, B is connecting to a member from B to A also and from B to C also. So we are having two members over here, BA as well as BC. So for member C, we can see C connects for member C to B and C to D. So now if you want to find out the stiffness, we know that we need to find the, or we need to know the far end conditions. So in this member BA over here, B is the near end and A is the far end. Since the far end is fixed over here, the stiffness will be equal to I upon L. So the value of L will be 4 meters for BA, that is the height or the distance, which will be equal to 0.25 I. So if you consider for member BC, B is the near end and C is the far end. Since the far end is an intermediate support over here, the intermediate support is also considered as an fixed support. So the stiffness will be equal to I upon L. I value they have provided here for BC, which is 2I. So this will be equal to 2I upon 8. The length is 8 meters over here for BC span. So this will be equal to 0.25 I. So if we come for member C to B, C is the rear end and B is the far end. Since B is an intermediate support, we are considering it as an fixed support over here. So for member CB, since it is the far end is fixed, we are considering it as a fixed support. We are having the stiffness as I upon L, which will be equal to again 2I upon 8, which will be equal to 0.25 I. Now for member C to D, C is the rear end and D is the far end. Since the far end is fixed, again the stiffness will be equal to I upon L. So here I upon the total length is 4 meters, which will be equal to 0.25 I. So now we have to take the summation of these two for the member or the joint B over here. So for joint B, the summation of stiffness will be equal to 0.5 I. Here also it is 0.5 I. So if you want to take if you want to get the rotation factor, then we need to just apply the value whatever we have got here. K is 0.25 for member BA and the summation of K is 0.5 I. So if we just apply the value over here, the rotation factor for member BA will be equal to minus 0.25 and here also minus 0.25. So the rotation factor for member BA is minus 0.25 and for member BC also the rotation factor is minus 0.25. And now if we calculate for member CB, the rotation factor will be minus 0.25, here also minus 0.25. So if you want to cross check here, the total of all the members should be equal to 1. So after calculating the rotation factors, since the frame is subjected for a lateral sway, we need to consider one more additional value we have learned from previous class. So apart from calculating the rotation factor, we need to consider one more value, that is the displacement factors. That is the displacement factors. So to calculate the displacement factor, we have to see how many stories we are having in this particular frame. This is a one bay and one story frame. So we are having one story. So in the table, I will consider first the story. And for that particular story, we have to see how many vertical members we are having. So we have to consider the vertical members over here. So the second in the table, I will consider it as the vertical members. And for that vertical members, I need to find out the relative stiffness, which is given by K. And then I have to consider the total stiffness, which is sigma K. And next I have to find out the displacement factor, which is represented by U dash. So U dash here is given by minus 1.5 into K upon sigma K. So this is the formula we are going to use to find out the displacement factors. So story, we know we are having one story, and if we consider the vertical members, we are having two vertical members, BA and CD. So we are having two vertical members, BA as well as CD. So now if you want to calculate the relative stiffness for BA, since the near end is B and A is the far end, so since the far end is fixed over here, the stiffness will be equal to I upon L. So I upon the total length here is 4 meters, which will be equal to 0.25 I. So here also for CD, the value remains same. Since the moment of inertia is I they have given, so the value is I upon 4, so 0.25 I. So if we take the summation of these two, we are getting a value of 0.5 I. So now, if we just calculate the value of the displacement factors, just put the value K upon sigma K, whatever we have calculated here. So the displacement factor we are going to get for vertical member BA is minus 0.75, and for vertical member CD, we have got a displacement factor of minus 0.75. So now the third step will be to calculate the rotation contributions and the displacement contributions through the iteration process. So for that I have considered a table over here where I have replaced the intermediate support with the help of the Kanis boxes. So as per the problem what we have considered, the frame, this is A and this is B over here. So here it is C and this is D as per the problem. So what we have to do in this Kanis table over here is we have to represent the fixed end moment whatever we have calculated in the first step. So the fixed end moment from A to B, we know it was 0. From B to A also it is 0. C to D it is 0 and D to C also it is 0. So we are getting fixed end moment from B to C, the value we have got, that is minus 375 kilonewton meter, and from C to D we had got a value of plus 225 kilonewton meters. So inside this box, we have to take the summation of the fixed end moment about that particular joint. So if we observe over here, this is 0 and this is minus 375. So if we take the summation of these two fixed end moment, we are getting a value of minus 375. Similarly, at joint C, we get a value of plus 225 kilonewton meters. So next, here inside this small box, we have to write the rotation factor whatever we have calculated in the second step. So the rotation factor for member B to A, we had got a value of minus 0.25. Here also from B to C, we had got a value of minus 0.25 for member B to C. The rotation factor is minus 0.25. So the rotation factor for member C to B, we have calculated it is minus 0.25. And for member C to D, the rotation factor is minus 0.25. Also apart from that, we have calculated the displacement factor for vertical member BA and vertical member CD. So that value we will just put over here, which we have got minus 0.75. So this value we have got over here. Here also for member C to D, we have got a value of minus 0.75. So this value we'll write over here. Now we need to calculate the rotation contributions, which is represented by M dash AB. Here M dash BA, this will be M dash B to C, M dash C to B, here M dash C to D, and here it is M dash D to C. So we know that the rotation contributions are only calculated for the intermediate supports and not for the end supports. So automatically the value of M dash AB for the end support rotation contribution and M dash DC will be equal to 0. Also apart from this one, since the frame is undergoing a lateral sway, we need to consider the displacement contributions into consideration. So for vertical member BA over here, we are having a, that is M double dash BA, the displacement contributions. So for vertical member C to D, it will be M double dash C to D. So these values we need to consider also. So now if we calculate for the rotation contributions first, we know the formula. So for rotation contributions, we have learnt M dash is given by U into summation of fixed end moment plus summation of far end rotation contributions. So this is the formula which we have learned from the previous classes. So see here, now if we calculate for M dash BA, so M dash BA, if we observe over here, the rotation factor for member B to A and B to C are same. So we can calculate M dash BA and M dash BC at a time because it is having the same rotation factors over here. So M dash BA will be equal to M dash BC, which is equal to the rotation factor now, which is minus 0.25, and the summation of fixed end moment. So the summation of fixed end moment here is minus 375 plus now total summation of far end rotation contributions. So for member, that is B to A at a joint B, which is the far end over here, I'll write the representation over here. See, this is the far end over here, M dash AB. Also M dash CB, this is the far end. Also we are having one more value, that is M double dash BA, which is the displacement contributions from B to A. So these three are the far end rotation contributions we need to consider. So for M dash AB, since it is an fixed support and the end support we are not taking it, so the value is 0 over here. So the displacement contributions we don't know, we need to calculate. So for the first cycle, this will be 0, and here also the far end rotation contributions M dash CB, we don't know the value. So this also will be equal to 0 over here. So we are getting a value of minus 79 point, sorry, we are getting a value of plus 93.75 kilonewton meter. So this is the value. So this value we have to write over here, that is 93.75. I will write in another color pen so it will be easy to follow. So 93.75. So 93.75, here also 93.75. So similarly we have to calculate the rotation contributions for M dash CB and M dash CD. So here if we consider M dash CB is equal to M dash CD. So it is also having a same rotation factor. So we will take the values identical. So it is minus 0.25, and the summation of fixed end moment over here is how much? That is plus 225 plus. Now here, which is the far end condition for this one here for joint C? For joint C, this one is the far end rotation contribution. Similarly, here M dash BC, this is the far end rotation contributions. Also M dash CD. So this also will be the far end rotation contribution. So these three value we need to consider. So for m dash dc, we know the value is 0, plus for m double dash cd, we don't know, we have to calculate, that is displacement contributions, so that will also be 0. But m dash bc, we are having a new iteration value over here, so this will be plus 93.75. So this gives a value of minus 79.68 kilonewton meter. So this is the value. So this value will provide over here, that is minus 79.68. So minus 79.68. So this is the value. Now after calculating the rotation contributions, we need to calculate the displacement contributions also. So to calculate the displacement contributions, so the displacement contributions, we know it is given by m double dash is equal to summation of m double dash t, that means at the top, plus summation of displacement contributions about the bottom. So this is the formula. So now if you want to calculate m double dash BA, this will be equal to, see here, about this value. Now if I want to consider this value over here, m double dash T. Also with this one, we need to calculate the displacement into the displacement factors also, that is u dash. So if you observe over here, the value of u dash we have got here, that is minus 0.75 into summation of the displacement contributions about the top over here. See, now if we take about this point over here, about the bottom it is 0 because it is a fixed end over here and it is the end support. So always at the bottom the displacement contributions are equal to 0. So if we take the sigma m double dash t, that is displacement contributions about the top, we are having a value. See here we are having a value now. This is the far end condition for m double dash BA. So we are having a value of 93.75. Also we are having a value of here how much? 79 minus 79.68 plus 0 plus 0. Why? Because here also it is 0 and about point D also it is 0. So m dash BA, since the displacement factors are identical over here, I will take m double dash BA will be equal to m double dash CD. So m double dash BA is equal to m double dash CD. We are having a value here, that is minus 10.55 kilonewton meter. So this is the value. So this value will provide over here, which is minus 10.55. So here also minus 10.55. So this is the first cycle we have completed. So we have to go on doing the iteration process until we are getting the similar values over here. So for that, what we can do here is, see here, we need not calculate everything, only we need to calculate the far end conditions. Whatever the changes we are getting or the new iteration value, only this much we can change over here. So here also this values only will change. So see here. So if we take for m dash BA and m dash BC over here, the rotation factor is minus 0.25, summation of fixed end moment is minus 375. Now if we consider the far end conditions, see here it will be 0. Also we are getting a far end condition here, we are having a new value, that is minus 10.55, and here if we consider we are having a new value, that is minus 79.68. So now this will be equal to, we are getting a value of 116.30 kilonewton meter. So this is the value. So now this value we will provide over here, 116, that is 116.30. Here also 116.30. So now for m dash CB and m dash CD, here the rotation factor is minus 0.25. The summation of fixed end moment is 225. Now the far end rotation contributions here is how much? We have got a new value 116.30, and here about point D to C it is 0, but about a value of m double dash CD we are getting a value of minus 10.55, a new value. So now this value will be equal to minus 82.68 kilonewton meter. So this is the answer, this is the value. So this value we'll write over here, that is minus 82.68 minus 82.68. So now if you want to calculate the displacement contributions over here, this is the displacement factor minus 0.75. Now a new iteration value we have got here, that is 116.30. Here also we have got a new iteration value which is minus 82.68 plus 0 about this point and plus 0 about this point over here. So we are getting a value of minus 25.21 kilonewton meters. So this value we will provide over here, which is minus 25.21. So here also minus 25.21. So now if you go for the third cycle, so just calculating for the third cycle, the rotation contributions. See here. So about m dash BA and m dash BC, if you observe over here m dash BA, the far end rotation contribution here is minus 82.68, and about this point we are getting a new value, that is minus 25.21. Any other values? So this is the far end rotation contribution m dash. So about this point will be 0. So we are having a value of plus 120.72 kilonewton meters. So this value we will provide over here, that is plus 120.72 kilonewton meter. Here also 120.72 kilonewton meters. So m dash CB and m dash CD, the far end rotation contributions we are having a new value 120.72, and here we are having a new iteration value, that is minus 25.21, and about this point here this is 0. So we are having a value of minus 80.12 kilonewton meters. So this value we will provide over here, that is minus 80.12 minus 80.12. So if you want to calculate the displacement contributions over here, for the displacement contribution if we take, we are having a new value over here, that is 120.72, and here we are having a new value minus 80.12 plus 0 plus 0. So 0 about this point and 0 about this point over here. So we are having a value of minus 30.45 kilonewton meters. So this value we will provide over here, minus 30.45 kilonewton meters. Here also minus 30.45. So if you observe the values over here, it is not similar, it is gone changing. So we have to continue the iteration process until we are getting the similar values. So I have calculated the values, I will just write over here. So in the fourth cycle, we are getting a value of 121.39. You please cross check. And here also it is 121.39. So for the fourth cycle M dash CB, we are getting a value of minus 78.98. Here also minus 78.98. And the displacement contributions for the fourth cycle, we are having a value of minus 31.80. Here also minus 31.80. So in the fifth cycle, I am having a value of M dash BA 121.43. Here also 121.43. And in the fifth cycle, for M dash CB and M dash CD, the value here is minus 78.58. So here minus 78.58. And the displacement contributions in the fifth cycle, we are having a value of minus 32.08. Here also minus 32.08. So in the sixth cycle, we are getting a value of again 121.43. Here it is 121.43. Here we are getting a value of minus 78.58, minus 78.58. And here we have got a value, the displacement contributions, minus 32.13. Here also this value I'll write over here, minus 32.13. So now it is almost similar over here. So if we go for the another cycle, we are going to get the similar values. So we can consider these values as the final displacement contributions and the rotation contributions to calculate the final end moments. So these values we will consider for the calculation purposes of the final end moments. So the last step here, see here. So the last step, it is step 4. So the last step will be to calculate the final end moments. So to calculate the final end moments, we know moment, final end moment from A to B will be equal to the formula fixed end moment from A to B plus 2 times the rotation contribution about the near end plus 1 time the rotation contribution about the far end plus also now we are having a value that is the displacement contribution, that also we need to consider, that is M double dash BA. So that value also we need to consider over here. So if I just apply the value over here, fixed moment about A to B is 0, about the near end about AB that is also 0 plus M dash BA. So M dash BA we have considered the value over here which is 121.43, and M double dash BA, the displacement contribution, we have got a value of minus 32.13. So this gives a value of moment about A to B. This will be equal to plus 89.29 kilonewton meters. So now similarly, if you calculate for M B to A, fixed end moment from B to A plus 2 times the rotation contribution about the near end plus 1 time the rotation contribution about the far end plus the the displacement contributions from B to A. So here also if we calculate, this is 0, the fixed end moment is 0 plus 2 times the rotation contributions, we have got a value here M dash BA 121.43 plus this is 0 M dash AB, it is 0 over here. Also we are getting M double dash BA, it is minus 32.13. So if we just calculate this one, we get a value of moment about B to A is plus 210.71 kilonewton meters. So now after calculating MAB and MBA, now we will calculate MBC and MCB. So I'll write the formula over here. This is fixed end moment from B to C plus 2 times the rotation contribution about the near end, that is B to C plus 1 time the rotation contribution about C to B. Here we are not getting for span BC, we are not getting any displacement contributions because the displacement contributions are only calculated for the columns, that is the vertical members, and not for the horizontal members, that is beams. So fixed end moment from B to C, we have got a value that is minus 375 over here, minus 375 plus 2 into M dash BC. M dash BC, if you observe over here, we have got a value that is 121.43 plus M dash CB. M dash CB, we have got a value over here, final rotation contribution, that is minus 78.58. So final end moment from B to C, we are having a value of minus 210.71 kilonewton meters. So if you observe over here, from B to A and B to C, we are having a similar and opposite moment. That means the calculation is correct. So next, if we calculate, after calculating fixed moment from B to C, so we are remaining with final end moment from C to B. So I will just write the values here I have calculated. You please cross check once. So the final end moment from C to B, we have got a value of plus 189.28 kilonewton meters, and the final end moment from C to D, we have got a value of minus 189.28 kilonewton meter. Similarly, moment about D to C, we have got a value of minus 110.7 kilonewton meter. So these are the values we have got. So now if you want to represent the final end moments as per the problem whatever we have taken, so this is the frame. So this is the frame we have considered over here. If we take this frame over here, sorry, this is point A, this is point B, this is C, and this is D over here. So what is the final end moments from point A to B? We have got plus 89.23. That means it is acting in the clockwise direction. So this value over here is 89.29 kilonewton meters. And from B to A, we have got a value of plus 210.71, which is rotating in the clockwise direction. Similarly, from B to C, we have got negative value, that is minus 210.71 kilonewton meters, and from C to B, we have got a value of positive plus 189.28 kilonewton meter, and from C to D we have got a value which is acting in the anti-clockwise direction, that is 189.28, and from D to C we have got a value negative. Here also it is negative, rotating in the anti-clockwise, 110.7 kilonewton meters. So this is how we analyze a frame which is subjected to the lateral sway with the help of Kanis method. So similarly we shall see few more problems related to Kanis method in the next coming classes. Thank you.